तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
In the last lecture, we acquainted ourselves with the concept of a network function in a general way and looked at the network functions pertaining to one-port and two-port networks. As far as a one-port network is concerned, we have two network functions to deal with, the driving point impedance and the driving point admittance functions. These are functions of S, but as I said, we refer to them simply as impedances. As far as two-port networks are concerned, there are four variables, terminal variables, V1, V2, I1 and I2. Any two of them can be expressed in terms of the other two, and we have several sets of parameters which characterize a two-port network as far as the terminal behavior is concerned. These are the Z parameters, the open circuit impedance parameters. The short circuit impedance parameters are the Y parameters, the H parameters, the hybrid parameters, and the transmission parameters are the ABCD parameters. We saw the definition of each one of these sets of parameters, and we also saw the consequences on the parameters arising out of the reciprocity theorem. That is, if the network contains purely bilateral and reciprocal two terminal pair elements, what are the restrictions on this? We saw that Z12 equals Z21, Y12 is equal to Y21, H12 equals minus H21, and the determinant of the ABCD matrix equals 1. Therefore, for reciprocal two-port, only three of these four parameters in each set are independent. So once we know three, the fourth one can be obtained easily. Now, on the other hand, there are some two-port networks which provide identical behavior whether you view it from port 1 or port 2. Then such two-port networks are called symmetrical two-port networks. That means the networks have a kind of symmetry with reference to ports 1 and 2. Now, if you have a symmetrical two-port network, the consequence is that the driving point impedance, whether you look at port 1 or port 2, is the same. Z11 equals Z22, Y11 equals Y22, and likewise in the terms of H parameters, the determinant of the H parameter matrix H11 H22 minus H12 H21, that is the determinant equals 1 and A equals D. So if a network is symmetrical and reciprocal, then two restrictions on these parameters are valid. Therefore, for a symmetrical reciprocal network, we have only two of these parameters in each set are independent, the other two follow from that. Now, based on these definitions of the various network parameters, let us work out a series of examples to illustrate the meaning of these various terms. Examples. Suppose I have a very simple network, two-port network, which consists of just one series element. Let us say the impedance of this is Z0 or the admittance of this is Y0. So one is the reciprocal of the other. A one port here with an impedance function Z0 of S or its reciprocal Y0 of S as the admittance function. 1, 1 prime, 2, 2 prime. Now, if you try to find out the Z11 for this, you keep this open circuited and try to measure the input impedance, that is infinity, because once you keep this open circuited, then input impedance is infinity. Z21 also turns out to be infinity, because if you want to drive a current I1 here, that I1 must go through infinite impedance, and therefore consequently an infinite voltage will be developed theoretically across port 2. So Z11, Z21 will be infinite. Similarly, it can be shown that Z12 and Z22 are infinity. So all the four parameters are infinite. That serves no useful purpose for us. So simply we say Z parameters do not exist. do not exist. What about Y parameters? The Y matrix. Now if you short circuit port 2 and try to measure the input admittance here, that is equal to Y naught, because after all the total impedance seen is that of this one port network only. Therefore the impedance is Z0, the admittance is Y naught. Therefore Y11 is equal to Y naught. So if you apply voltage V1 here, the current that flows here is Y naught times V1. That is the current that flows here, that is I1. The same current flows here also. That means in our definition I2 is this current. This is I1, this is I2. So I2 happens to be minus Y naught times V1. So the definition of Y21 is I2 divided by V1 when 2 prime is short circuited or the port 2 is short circuited. Therefore Y21 equals minus V naught, minus Y naught. And since this is a symmetrical network, you find the same type of element arrangement whether you from port 1 or port 2. Y22 is also the same. This is also a reciprocal element because this is a bilateral type of impedance. Therefore this is minus Y naught. So a series element constituting a 2-port network will have a short circuit admittance matrix given in this fashion. You can calculate by similar reasoning the hybrid parameter matrix. The H matrix for this turns out to be 1 over Y naught or Z naught, 1 minus 1 0. Again this is a symmetrical network. You have 1 minus 1, H12 is equal to minus H21. The determinant of this is Z0 times 0 minus of product of 1 and minus 1. The determinant of H matrix is equal to 1, and that is a consequence of symmetry as we have already explained. Therefore it all adds up. The transmission matrix, the ABCD matrix for this can be computed from the definitions of the ABCD elements. This turns out to be 1 1 0 Z0. All these Y naughts and Z naughts are functions of S, of course, in a general case. So in this simple example we have Z parameters do not exist, Z matrix does not exist, but the other matrices, other parameters do exist, and these are the values. Now let us take another simple case where we have a shunt element 1 1 prime 2 2 prime. Now if you short circuit this and measure the input admittance, that is going to be infinity, and so it turns out that all the Y parameter elements, Y parameters are going to be infinity. Therefore we can say Y matrix does not exist. What about Z matrix? If you keep the port 2 open and measure the input impedance that is equal to the impedance of this element. So let us say this is Z0 or its admittance Y0. So the input impedance when port 2 is open is Z0. Keeping port 2 open, if you drive a current I1 here, the voltage that is developed across port 2 is the same as the voltage that is developed across this impedance, which is I1 times Z0. Therefore V2 divided by I1 when I2 is 0, that is the value of Z21, and it happens to be equal to Z0. Therefore this is also Z0. And again this is a symmetrical reciprocal network. If you calculate Z22 and Z12, they will also be the same. So for a simple 2-port network constituted by one shunt impedance, this is the Z matrix for this. The H matrix for this can likewise be computed 0 1 minus 1 Y0. Again it's a symmetrical network, its determinant is going to be 1, and H12 is equal to minus of H21, which is a consequence of reciprocity. The transmission matrix for this will be 1 0, will also have a very simple form 1 0 Y0 and 1. And again you see the determinant of the transmission matrix AD minus BC is equal to 1. That comes as a result of the reciprocity of this network. Let us now take a third example. Here we will complicate this a little bit. Let us consider a T network consisting of three impedances, impedance functions that is. Z1, Z2, Z3. These are all functions of S. So three one-port networks connected in a T formation. This is called a T network because the three impedances have the configuration corresponding to a T, letter T. Therefore, this is a T network. And if Z1, Z2, Z3 are functions of S, if you want this particular configuration enables us to determine the Z matrix of this two-port network very conveniently. Z11 is the impedance seen at port 1 keeping port 2 open. So if you drive a current I1 through this one port terminals, that current passes through these two impedances because port 2 is open, and it develops a voltage Z3 times I1 across port 2, and across port 1 it develops Z1 plus Z3 times I1. Therefore, the Z matrix for this will have Z11 is Z1 plus Z3, Z21 is simply Z3 because a current I1 flowing through this will develop a voltage Z3 times I1 across this shunt network, shunt branch, which is also the voltage across port 2. So Z3 will be the Z21 element, and when you do the same operation, connecting a current source here of I2 and keeping this open, the voltage that is developed across port 1 is Z3 times I2. Therefore, Z12, which is V1 divided by I2 when I1 is 0, it happens to be Z3. Therefore, this is Z3. And looking in impedance here when port 1 is open is the sum of these two, which is Z2 plus Z3. So you observe that in the case of a T-connected configuration of a two-port network, the values of the Z parameters can be computed with surprising ease. Very simple. In a converse fashion, suppose you have a complicated two-port network. Let us say a highly complicated two-port network. Maybe like this, a general two-port. Now, this general two-port network will have some Z parameters. You can compute them using the various methods of network analysis that are available to you. But if that general two-port network has got a Z matrix which is equal to Z1, it is given by Z11, Z12, Z21 and Z22 in our general configuration, we can form an equivalent T network for this in this form. So this is an equivalent network which has identical terminal behavior as the original network. So what is meant by an equivalent network? If two networks are equivalent, then the terminal behaviors of the two networks are identical. So in the case of a two-port network, the relation between V1, V2, I1 and I2 will be identical in both cases. So if I have this general two-port described by a Z matrix, I can describe the terminal relations of the general two-port by means of this equivalent network. By writing this as Z11 minus Z12, this as Z12, and this as Z22 minus Z12. So that means when I look from this side, the total impedance when keeping port 2 open is Z11 minus Z12 by Z12. Therefore, Z11, which is the driving point impedance of this network, I use that value here. That means all these parameters are those which relate to the general network. If I calculate them and then incorporate three impedances having these values, this particular network will have the same terminal relations as this original network. All this is on the basis that this is a reciprocal two-port network in which Z12 is the same as Z22. That means general two-port network which is reciprocal. This is very important. If this is not reciprocal, that equivalent will not be valid. So we have a general reciprocal two-port network which follows the reciprocity theorem, which means Z12 is equal to Z21, and in that case this is an equivalent configuration for the general two-port network. So instead of dealing with this complicated two-port network, we can always replace this by its equivalent and use this for any analysis problem. In a similar fashion, if I have what is called a pi network, suppose I have a configuration like this with 3 elements. Let us say this is YA, this is YB, this is YC. Then for such a network, calculation of the Y parameters turns out to be very convenient. So this is the port 1, 1 prime, 2 prime. The Y parameters for this is very convenient to calculate, because when you short circuit this and measure the admittance at port 1, that is the parallel combination of YA and YB, because once this is shorted, YA and YB come in parallel, and that is the total admittance seen at port 1. Therefore, Y11 equals YA plus YB. Now, what is the current in port 2 when it is shorted? What is I2 in terms of V1? When you have applied voltage V1 and short circuit these terminals, this entire V1 appears across YB. So the current in this direction is V1 times YB. But our reference direction for current I2 is in the opposite direction. Therefore, I2 divided by V1 turns out to be minus YB. Therefore, this will be minus YB. And similar arguments by applied when you short circuit port 1 and apply a voltage across port 2 will lead us to the result that Y12 is equal to minus YB, and this is YB plus YC. So when you have a pi network, this is called these 3 are in the form of a pi, the letter pi, the symbol pi here, and this is called a pi network. So when you have a pi network, usually referred to as pi network, this is called a T network. So when you have a pi network, the calculation of the Y parameters turns out to be very convenient. And we have a negative sign here. That is important to note, because we have taken the reference direction in this fashion, and therefore when you apply voltage V1, current actually flows in this direction. Suppose you have a pure resistance, the current will flow in this direction. If you have a DC source and a resistance, the current will flow in this direction. But since the reference direction is opposite sense, it turns out that as far as the transfer admittance in a Y matrix is concerned, you will have a lot of negative coefficients. So that has to be kept in mind, that as far as the network has a 3-terminal configuration, that means there is a common ground between port 1 and 2, it turns out that the coefficients in the transfer admittances will turn out to be negative. It may or may not be so when you have a 4-terminal type of 2-port network. For example, if I have a 2-port network in this fashion, suppose this is port 1, 1 prime, and this is port 2, 2 prime. There is no common connection between 1 prime and 2 prime. In such cases, the transfer admittances may have positive coefficients or negative coefficients or both. But on the other hand, if it's a 3-terminal 2-port, you have negative coefficients like this. So this is. So conversely, a general reciprocal two-port can be modeled by the following equivalent circuit. By the following equivalent circuit. That is, just as we had found out an equivalent circuit for a reciprocal general 2-port network here, you found out an equivalent circuit in this form. Similarly, when you have a general reciprocal 2-port network, we can find out the equivalent circuit in terms of the Y parameters in this fashion. you observe that the shunt element here is minus of the series element, series impedance here, series branch here as an admittance which is equal to the negative of y12 or y21. Therefore, I can write this as minus y12 of S. And when you short circuit this, the total admittance seen from port 1 must be y11. Therefore, this must be whatever you are having here is equal to y11 of S plus y12 of S. So this one port network must have a total admittance y11 of S plus y12 of S. So this plus this, when you short circuit this, will provide a total admittance at port 1 which is equal to y11 of S. Likewise, this admittance will be y22 of S plus y12 of S. So that is the configuration. So we have seen from these two examples that there is a duality between them. If we have a T network, you can find out the open circuit impedance parameters quite conveniently, or in a general two-port reciprocal network can be modeled in terms of the Z parameters by an equivalent T network quite conveniently. Similarly, if you have a pi network, the Y parameters are easy to compute, or conversely, a general reciprocal two-port network can be modeled by a convenient equivalent circuit in the form of a pi network using the Y parameters as shown here. This is a slightly more complicated example. Let us say that we are interested in finding out the Z parameters of this two-port network. We have seen earlier that if the network is in the form of a T network, then the evaluation of the Z parameters is quite convenient. However, this configuration is not in the form of a T. On the other hand, if we convert this delta configuration of a 1 farad capacitor and two 1 ohm resistors by means of convert this into a star like this, then the whole network falls out into the form of a T network. So let us try to do that, convert this delta into an equivalent star. So delta to star conversion. Now the rules for this conversion follow exactly the same lines as we have in the case of resistive networks or in the case of impedances under AC circuit analysis. So however, we have to use the generalized impedances in this case. So this delta, if it is converted into a star, will have three generalized impedances like this, and of course you have this 1 ohm resistance here. So this will be 1 prime, 2 prime. So this delta will be converted into this equivalent star, and we can find out the open circuit impedance parameters of this altered configuration. The terminal conditions will remain the same because whatever changes have been brought about are internal to the two-port. The impedance of this is obtained by the product of these two impedances divided by the sum of the three impedances. Therefore, the impedance of this will be 1 upon S, that is generalized impedance of this, times 1 divided by the sum of the three impedances, which is 2 plus 1 over S, which will be of course 1 upon 2S plus 1. By symmetry, this will also be 1 upon 2S plus 1. That is the impedance of this box. The impedance of this box, however, is the product of these two impedances divided by sum of the impedances. So this 1 times 1 divided by 2 plus 1 over S, this will be S upon 2S plus 1. And of course this 1 ohm resistance will remain. So now the entire network now is in the form of a T network, and we can find out the open circuit impedance matrix of this forthwith without further ado. So ZOC of S of this would be the driving point impedance at port 1 is the sum of this impedance plus this impedance plus this impedance. This is 1 over 2S plus 1, this is S over 2S plus 1. Therefore, S plus 1 over 2S plus 1 plus 1 of course, which will be of course 3S plus 2 over 2s plus 1. That is Z11. By symmetry, Z22 is also 3s plus 2 over 2s plus 1. Z21 and Z12 is given by this impedance of this shunt branch. S over 2s plus 1 plus 1. That will be 3s plus 1 over 2s plus 1. That one will be the open circuit impedance matrix of this two-port network. On the other hand, let us imagine that we are interested in finding out the y parameters of that. To find out the y parameters, it is most convenient if the network is in the form of a pi. So how can we convert this into an equivalent pi? The answer is quite straightforward. We have 3 resistors connected in star. If we convert them into an equivalent delta, we have one branch coming in parallel with 1 farad capacitor, another branch coming in parallel with the first port, a third branch coming in parallel with the second port. The whole configuration will be in the form of a pi. So let us do that. So star to delta conversion, if you do that, we retain the identity of the 1 farad capacitance, which has got a generalized impedance 1 over s. In addition, these 3 resistors are connected into an equivalent delta. So that will be the altered configuration. The impedance of this 3 1 ohms in star is equivalent to 3 ohms in delta. So these are all the generalized impedances are 3 ohms each. So that will be the configuration that we have for the pi network that is obtained by converting the star into an equivalent delta. So what are the y parameters for this? This is a short circuit impedance matrix for this now. The driving point impedance at port 1 is obtained by short circuiting second port and looking at the impedance as seen from port 1, which will be, this is 3 ohm resistor, its admittance is 1/3, the admittance of this is 1/3, and that is in parallel with a capacitor of admittance S. So all these 3 elements come in parallel because 2 prime is effectively short circuited. So port 1 sees a admittance which is the sum of this impedance plus this admittance plus this admittance plus this admittance. That will be 2/3 plus S, which is 3s plus 2/3. And by symmetry, the impedance seen from port, admittance seen from port 2 as well will be 3s plus 2/3. Now what about the transfer admittance? Suppose you short circuit this, apply voltage here. The current that flows in 2 is limited by the admittance of this parallel branch, because this is ineffective because it's short circuited, and the current here we don't care what it is, we are interested only in the current flowing in this. So the current flowing in this will be the applied voltage times the admittance of this parallel combination. That will be 1/3 is the admittance of this and S is the admittance of this. So 1/3 plus S times V1 will be the current flowing in this direction. But our port reference is in this direction. The current will be measured always with this reference sign. Therefore, we must put a negative sign out in front. So Y21 will be minus of 1/3 plus S. That will be minus of 3s plus 1/3. And Y12 likewise will be minus 3s plus 1/3. That will be the admittance, short circuit transfer admittance of Y12. Now we observe here that Z12, Z21, Y12, Y21 are all of them having the same 0. S equals minus 1/3 makes this 0, this also 0, and so does it make the transfer impedances Z21 and Z120. Zeros of transfer functions are called zeros of transmission. Essentially, they are the values of the complex frequency for which if you apply a signal as an input with that complex frequency, the output turns out to be 0. Therefore, they are called zeros of transmission. And the zeros of transmission are inherent for a particular network. So if you are having a system function HFS, a generalized system function, a general transfer function, if you apply an exponential input signal e power s naught t, and the forced response of that is of course hs naught times e to the power of s naught t is the forced response, then if hs naught is 0, then s naught is said to be a zero of transmission. And this zero of transmission is inherent for a particular system. So with minor exceptions here and there, if there is a particular zero of transmission associated with a transfer admittance, that will also be the zero of transmission with the transfer impedance, transfer voltage ratio, transfer current ratio, and so on and so forth. So this HFS can be any type of transfer function for a signal flow from input port 1 to port 2. In this case, in our case, there is only one zero of transmission, that S naught happens to be minus 1/3. So if you drive this two-port network at port 1 with an exponential signal e power s naught t, where s naught is minus 1/3, then the forced response at the output is 0. A word about this zero of transmission or zeros of transfer function. We know that the poles and zeros of driving point functions have certain restrictions as far as their natural response is concerned. From the point of view of stability of a passive network, we already observed that the poles and zeros of passive transfer driving point functions of passive networks must be in the left half plane, and if they are on the imaginary axis, they should be simple. So from the point of view of stability of passive networks, the poles and zeros of driving point functions have got certain restrictions. Same restrictions also are valid for the poles of transfer functions. For example, this transfer function has a pole at s equals minus half. So poles and zeros of transfer functions, the poles of transfer functions must have the same restrictions as the poles and zeros of driving point functions as far as passive networks are concerned. But as far as zeros of transfer functions are concerned, there is no such restriction. Even for passive networks, we may find the zeros of transmission anywhere in the complex S plane. They need not be restricted to the left half plane. They can be in the imaginary axis. They can be in the right half plane, and so on and so forth. So absolutely no restrictions on the zeros of location of zeros of transmission or the zeros of transfer functions. The poles of transfer functions, however, are restricted in the same way as the poles and zeros of driving point functions. So far, we have been considering only reciprocal networks. So let us consider a two-port network constituted by dependent sources. We have two dependent current sources. The current here depends upon this voltage, the current here depends upon this voltage. So we have for this network I1 equals G times V2. I1 of S is G times V2 of S. And I2, which is the current in this direction, is minus of GV1, so minus GV1. So these are the two conditions on the terminal variables. Therefore, the Y matrix for this will be I1 equals G times V2 and I2 equals minus G times V1. So that means I1, I2 are given by this matrix 0 G minus G 0 multiplying V1 and V2. So you observe that this Y matrix is not, the off diagonal elements are not the same, that means this is not reciprocal. So when we have dependent sources in the two-port network, the reciprocity relationship may not be valid. In fact, this is what is called anti-reciprocal. If this network is reciprocal, we expect these two to be equal. This is exactly the negative of this. So this is called anti-reciprocal. Such a two-port network constitutes what is called a gyrator. This is a two-terminal pair, two-port, lossless, anti-reciprocal device which can be constructed with active elements. This is one element. This is used in active network synthesis design of active filters, but we will just note the terminal relations and leave it at that. Let us take another example, slightly more complicated. Suppose we have this is a model of some active circuit. We have Gm times V1. We have resistance Rd and finally a capacitance Cd. So this is 1 prime, 2 prime. V1, I1, V2 and I2. We can calculate the Y parameters for this quite conveniently. So let us do that. Y11, you short circuit V2 and measure the driving point admittance. Once you short circuit V2, there will be no currents in Rd and Cd, so you can forget about that. And the impedance, the admittance as seen from port 1 is the admittance of this plus the admittance of this, because these two are now coming in parallel, and that what constitutes the current here. And whatever current is generated in this dependent source will flow through the short circuit GMB1, because that is the path with the least impedance. So Y11 will be the admittance of this plus the admittance of this. So 1 over Rg plus Cc of S. That is Y1. Y21, the current in this I2 short circuited current in the short circuited terminals, when applied voltage V1 is there, V1 drives a current through Cc like this. Therefore, there is a current Ccs times V1. In addition, we have a current through this dependent source GMV1 going like this. And since the direction, positive reference direction for current I2 is in this direction, so you have that current divided by V1 will turn out to be Gm minus CCFS. That is your Y21. Gm minus CCFS, that is Y21. Y22, if you short circuit the port 1, apply a voltage V2 and measure the current in the driving terminals, that current will be constituted by the current flowing in Rd, Cd. Since V1 is shorted, the current source strength is 0. Therefore, this is open circuited. You have a current passing through the coupling capacitor Cc through these terminals. Therefore, the parallel combination of this and this constitute the total admittance. So you have 1 over Rd plus CDS plus CCS. That is your Y22. Y12 is the ratio of current flowing to the shorted terminals in this direction divided by V2. So V2 drives a current through Cc in this direction, which is CCS times V2. So the current in the direction, reference direction for I1 is minus CCS times V2. Therefore, Y12 is minus CCS. Notice here once again, Y12 is not the same as Y21. This is because this is not a reciprocal two-port network because of the presence of the control source GMBM. So when we have control sources present, then reciprocity relations will not be valid. This is an active two-port network, and reciprocity is not valid. We have seen in these examples, in some of the earlier examples, that for a two-port network, one set of parameters may exist, another set may not exist. We have seen that in the case of a pure series branch, Z parameters do not exist, but other parameters do exist. In general, it may be that one set of parameters may exist, others may not. So for a very simple case, suppose I have a two-port constituted by two lines like this. These are two lines flowing right through from port 1 to port 2. You will find that all parameters except the ABCD parameters exist. So in this case, we have V1 equals V2 and I1 equals minus I2. Therefore, the chain parameters or the ABCD parameters exist, which is equal to 1, 1, 0, 0. Other parameters do not exist. You won't have X, you won't have Z parameters, you will not have Y parameters, you do not have H parameters for this two-port network. Now, we have constructed equivalent circuits of a two-port network in terms of Z parameters and Y parameters. And we said those two equivalent circuits in terms of T configuration and pi configuration are valid for a reciprocal two-port. Now what happens if we have a general two-port of this with a lot of active elements present, and if we want to find out the equivalent circuits for such situations, then we will have to model the equivalent circuits in terms of active elements. So the general equivalent two-port networks, general equivalent circuits in terms of active elements can now be given. We can say for Z parameters, you can write Z11 plus a voltage source which is equal to Z12 times I2 V1, and likewise you have Z22 I2 plus an equivalent, a source here which is a dependent voltage source which is Z12 times, Z21 times I1. That is an equivalent circuit in terms of Z parameters for a general, not necessarily reciprocal network. In terms of Y, you have Y11 V1 plus a current source which is equal to Y12 V2. And this is port 1, and for port 2 you have Y22 V2, that is the current here, and you have Y21 V1. That is the two-port network which will be an equivalent circuit in terms of Y parameters for a general two-port. And for in the case of ABCD matrices, you can write this in this form. You have A minus 1 upon C, this is an impedance of this. This is D minus 1 upon C, that is also an impedance. 1 over C is an impedance. And in addition, you can have a dependent source which is AD minus BC minus 1 divided by C times I2. So if you analyze this network, you will find out that it will answer the terminal relations of a two-port in terms of the ABCD parameters. V1 equals A times V2 minus B times I2, etc. And for a reciprocal network, this becomes 0 because AD minus BC equals 1. Therefore, this dependent source will vanish. In the case of H parameters, the equivalent circuit would be like this. We have V1 equals I1 times H11, that is a impedance, plus H12 times V2. So it's a voltage source, dependent voltage source, which depends on the value V2, and H12 is a dimensionless factor. On the other hand, the current I2 will be H21 times I1. So this is a current source of value H21 times I1 in parallel with an element whose impedance is 1 over H22. So if this is V2, the current here is H22 times V2, therefore the total current is H22 times V2 plus H21 times I1. So this is a current source whose current ratio is H21, and this is a voltage controlled voltage source whose value is H12 V2. So that is the configuration which gives an equivalent circuit of the two-port network in terms of H parameters. So these are the general equivalent circuits which can be made use of for analyzing a two-port network. Instead of either you can use the equations or these equivalent circuits. When dealing with two-port networks, we often use network functions other than those which I have already discussed. In this particular example, we have port 2 open, we apply an input voltage V1. The ratio of V2 of S to V1 of S under open circuit conditions is called the open circuit voltage transfer function in the forward direction. That is, if the signal is going from port 1 to port 2, and it can be shown that is Z21 by Z11. For example, you have V1 equals Z11 I1 plus Z12 I2, and V2 equals Z21 I1 plus Z22 I2. And when I2 is 0, these two terms get cancelled out. The ratio of V2 to V1 is Z21 over Z11. Likewise, you can show that this is also equal to minus Y21 over Y22. This can also be shown to be 1 over A or minus H21 by delta H. Similarly, if we keep port 1 open and apply a voltage to the port 2, so V1, this is called G12 of S, V1 of S over V2 of S, when I1 is 0, that can be written as Z12 over Z22 minus Y12 over Y11 is the delta T over D, where this is the determinant of the transmission matrix, is also equal to H1. So this can be, we can work this out, yes. Often we may also be interested in finding out the short circuit current ratio. That means you apply a certain current I1 here and measure the current I2 under the short circuit conditions. So you write this alpha 21 of S is I2 of S over I1 of S when V2 is 0. That is called the short circuit current ratio. And you can show that this is equal to Y21 over Y11 equals minus Z21 over Z22 equals minus 1 over D equals H21. And to complete this picture, you might have a situation where you want to find out the ratio of I1 to I2, when V1 is 0. This is alpha 12 of X, and this can be shown to be Y12 over Y22 minus Z21 minus Z12 by Z11 equals minus delta T over A equals minus H12 over delta H. The important thing to note in this, one important thing that we can note is that the transfer voltage ratio in the forward direction, which is Z21 over Z11, will turn out to be the negative of the short circuit current ratio in the opposite direction, minus Z12 over Z11, because Z12 is the same as Z21 for a reciprocal network. So for a reciprocal network, we can say for a reciprocal network G21 equals minus alpha 1 2. The open circuit voltage ratio in the forward direction is the negative of the short circuit current ratio in the reverse direction. We cannot say that G12 is equal to G21 because when you are measuring G21, you are keeping this open and you are applying a voltage source. This is V2 over V1 to find out G21. On the other hand, when you want to measure G12, you are keeping this open and you are applying a voltage here. So this is V1 divided by V2. You observe that in the natural configuration, natural state of the system, when you short circuit this, port 1 is shorted, port 2 is open. In this, port 2 is shorted, port 1 is open. So the natural state of the two networks before the excitation is introduced is different. Therefore, even though you may have reciprocal elements here, it does not follow the reciprocity theorem because the natural states of the two networks are different. One is short circuited here, kept open. The other is short circuited here, and this is kept open. Therefore, G21 is not equal to G12 is not equal to G21 even in the case of a reciprocal network. On the other hand, for a reciprocal network, G21 equals minus alpha 1 2. So in this lecture, we have expanded our knowledge of the two-port network parameters. We considered various examples, saw the consequences of reciprocity and symmetry on the values of the network parameters. We saw that when we have dependent sources inside the network, reciprocity property is violated. And that particularly occurs when we have active elements inside. And then we also saw that in the case of open circuit at port 1, we can define what is meant by an open circuit voltage transfer ratio G12, which can be expressed in terms of Z parameters or Y parameters. Similarly, the short circuit current ratio can be expressed in terms of these parameters. And we saw a reciprocal network, the open circuit voltage ratio in one direction is the negative of the short circuit current ratio in the opposite direction. We'll continue our discussion in the next lecture.